So welcome back, children. In the previous video, we were talking about the LCR circuit and resonance. Let me summarize it again quickly. So if you have an LCR circuit, say something like this, R, L, and then C, and if you drive this circuit with an AC voltage V is equal to Vm sine omega t, and there will be a certain current I which will flow in this circuit. By keeping the voltage, the maximum minimum voltage, voltage at the same level, and if I change the frequency of this power supply, then I will get different currents in this circuit. The reason is because XL is equal to omega L, and then XC is equal to 1 by omega C. So if this changes, and for the same L and same C, I can get different XL and XC values. So even though the voltage has the same maximum value, this is time, this voltage, for different frequencies, I'm going to draw them for different frequencies. So suppose I have this, something like that. So all these different frequencies will, even though you have the same Vm and minus Vm here, the XL will be different because you have different frequencies at which you are giving this voltage. So that is what we saw. And because this changes, XL and XC changes, Z will change, because Z is basically square root of R squared plus XL minus XC whole squared. XC minus XL whole squared. So this is matter. Okay. So what is going to happen now is that since Z changes, the current in the circuit will change based on the frequency. Okay? So the current will be like this. I'm going to draw it for 3 frequencies now. Okay. So this could be one frequency. Okay. And this could be a different frequency, and the third could be this. Okay. So I say, so this is for one frequency omega 1, and this is for omega 2, and this is for omega 3. So I get IM1, and then IM2, this is IM3, and so on. So for different frequencies, for the same input voltage, I can get different currents in the circuit. Here it is I versus time. So normal, this voltage versus time graph, this is current versus time graph. So you can see that the graph contains different frequencies. Okay, and if we just take the maximums and draw the graph for maximums, there is a particular frequency which we call as omega naught, for which I get the maximum. Okay, I'm going to take this maximum and draw the graph against the frequency. So this will be Im max. So maximum. So for a particular frequency, I will get the maximum value, And for omega 1, I make it something else, omega 2, I make it something else. And the graph would be like this. Okay. So this could be omega 1, this could be omega 2, omega 3, maybe this is omega 4, omega 5, omega 6, something like that. Okay, so this is omega. So this is current. Yeah. So for different omegas, I get different maximums. So I'm going to plot that curve. So this is what we saw. Okay. Now the question asked us, what's the use of all this? Why should you worry about resonance? Why are we even doing it? The answer is that this is a very important phenomenon, and this is a phenomenon we use to tune into Sun TV and to tune into Raj TV, KTV, or even your cell phone signals. The reason why you get a call and then your cell phone rings is because there is resonance in the circuit, the cell phone circuit. I'll explain now. Even why we are able to see things is because of resonance in our eyes. The same principles apply everywhere. Why we are able to see certain frequencies in the electromagnetic spectrum. We are able to see blue, we are able to see red, we are able to see orange, yellow, and all these different colors. But why are we not able to see the cell phone signals or the ultraviolet signals? Why are we not able to see this? And that is because we have a certain range over which our eyes resonate with the electromagnetic spectrum. And beyond those frequencies, there is no resonance that is taking place in our eyes. And that is the reason why we are not able to see other colors, but only these colors. So the reason why we are even seeing something is because of resonance. The reason we are receiving a call on our cell phone is because of resonance. And why we are able to switch among channels on our TV or radio is because of resonance. And we'll explain that now. And now we are going to discuss how we are able to tune into a particular TV station. Okay. See, every TV station in the world, or channel in the world, they send out electromagnetic radiation. Just like the sun sends out light, which is also electromagnetic radiation. Every TV signal sends out electromagnetic radiation. They do that at a frequency which is specific to that TV station. Sun TV will transmit their signals at certain frequency, and Raj TV will transmit their signals at a different frequency, and NDTV will transmit their signals at a different frequency. So all these electromagnetic radiations are around us, and on top of these electromagnetic waves, we also have the cell phone signals, and each mobile phone will have its own frequency. Your number will have a frequency, my number will have a different frequency, and somebody else's number will have another frequency. So all of us have different frequencies. So when you hold a cell phone in your hand, actually you are doing what the TV stations or the radio stations do. You are transmitting signals at a certain frequency. So if I stand here, I am surrounded by these millions, billions of frequencies, even trillions of frequencies. It's not just the cell phone signals and the TV stations which are around me. The sunlight, different frequencies. It's around me. and the light from the other stars, they are also around us. There is ultraviolet radiation. There are different frequencies around us. So you are immersed in multitude of frequencies of electromagnetic radiation. Okay, so it's all there around us. With this background, I'm going to draw an LCR circuit. So this is called as a tuning circuit in your TV or your radio. Okay? So the tuning circuit is an LCR circuit you have here. It's like this. So you have a resistor, and then an inductor, and also a capacitor. So you have R, you have L, and then C. This is what you have here. Okay? And what you need now? You need a source to drive this. Correct? Okay. Here you are going to have an antenna. Something like this. This is the antenna. Antenna is nothing but two wires, okay, separated like this. You have different types of antennas. You have parabolic antenna, which you call as a dish, and you may have wire antennas. But ultimately, an antenna is basically a dipole. Okay? It's like you have wires. There is one end here and there is another end here. Okay, so this is what your antenna is. So now, this is a circuit, and this is kept. Suppose this is kept here, and this is hit by millions and millions of radio signals, right? The electromagnetic signals from around the universe. Okay, so there is a Sun TV signal sitting here. There is a Sun TV, and there is also Raj TV signal, and there is also NDTV, and there is also the sun itself. The light also hits. All these things are hitting here. Okay. So you have electromagnetic radiation here, which means that there would be an electric field. So in that electric field, the free electrons in this conductor are present. So they get sloshed around by the changing electric field of these signals. So it is like this. It is like you have the circuit, and then you have one EMF from the Sun TV, this is Sun EMF, and there is another EMF from Raj, and there is another EMF from NDTV or something. Okay, so you have millions of sources driving this, because there is an electric field. Because these are all electromagnetic radiations, there is an electric field. So those electric fields will make the free electrons in the antenna move around. And look at this. This is more like a capacitor, if you can recall. So then what happens is that this will go, the free electrons in this antenna will go up and down, and sometimes it is positive, sometimes it is negative. This voltage that comes from the Sun TV or even Raj TV or any other electromagnetic source, and that would make a current to flow in the circuit. Okay? So all these signals, all these different signals will try to send their own current in the circuit. So this is equal. Okay? So which signal will send send the maximum current in this. So that is, imagine this is I. So this I is sum of I1 plus I2 plus I3 plus I4 and maybe I1 billion. Okay, something like that. I1 billion. So all these things sending, all these electromagnetic radiations are trying to send current through this circuit. But you have R, you have L, and then you have C. Depending on the frequency, the values of this current will be different. That is what we saw. Because there is an XL for Sun TV, but it is not the same XL for Raj TV. Because Sun TV frequency is something and Raj TV frequency is something else. So even though I have the same inductor L, it will offer a different reactances to different signals because their frequencies are different. So if Sun TV is omega 1, then this inductor will offer one reactance to Sun TV. And this is omega 2, the same inductor will offer a different reactance to Raj TV and so on. For all these billions of signals, then this inductor is going to offer a different reactance. And the capacitance will do the same thing. So the Xc will also change based on the frequencies. So the impedance of this circuit will be different for different frequencies. For Sun TV, there will be one impedance. For Raj TV, there will be different impedance. So the current will also change. And which frequency, which channel will have the maximum current flowing through this? It is the channel that has the same frequency as the natural frequency of the circuit, LC. Okay? We know that the natural frequency, omega naught of the circuit, actually 1 by root LC. If there is a frequency that matches this frequency, then that will send the maximum current. And all the other frequencies will send lower current than this. So if I draw a graph for these different frequencies, whichever channel that has maximum, that has the same frequency as this circuit LC will send the maximum current. So this will be IM max, and all the other things will send lower currents. So suppose this LC matches with Sun TV, then I get maximum current for Sun TV. And suppose this is the frequency of Raj TV. Okay, this is Sun, this is Sun, this is Raj, omega. Okay, omega Raj. And this could be omega, this is NDTV omega. NDTV omega. Okay, this is, or this could be even DD, Doordarshan. Okay? This is DD omega. So all these different channels will be sending different currents in this, and in this case the Sun TV is sending the maximum current. So this circuit will have maximum current for Sun TV at this point in time. So then I will tune into Sun TV. Okay? So suppose I change the capacitance value. Suppose my capacitance value is changeable. Okay? By changing the area of the plates of the capacitor, then I can change the capacitance value. If I change the capacitance value, now I have a different omega naught, not the same omega naught. Initially I had one capacitance value, now I change the capacitance value by changing the area of the plates. Then I'll have a different capacitance, and for that capacitance, since inductor remains the same, I will have a different omega naught. Now, if you want to tune to Raj TV, then I will change the capacitance value such that this root LC will be equal to the Raj TV. So in that case, Raj TV will give me the maximum current. Now this will become my omega naught. Okay? This will become, because of the change, this will become omega naught. So now my curve will be something like this. Notice now, initially sun was giving the maximum current. Now I change the capacitance. So since I change the capacitance, the natural frequency of this circuit has changed, and that matches with Raj TV. So the Raj TV signal will send the maximum current in the circuit. Now you see the Sun TV is sending only so much current. So it is so less now. Okay? And if I want to tune to NDTV, then I change this again. So in that case, then my omega naught, the natural frequency of this circuit, will be equal to the frequency of NDTV. So in that case, then I get the graph like this. So now notice when I tune to NDTV, then Raj TV has only sending only this amount of current, and Sun TV is sending only this amount of current. But what sends the maximum current? This is it is NDTV. Okay. So this is what is called as tuning. So when you turn the knob of a radio, then that is what you are doing. Actually, like you are, there is a set of parallel plate capacitors. Okay, and when you turn the knob, then this will come out. So the area between the plates will reduce. If both the plates are together, then it's a greater area. And as you turn the knob, then the area will, the plates will try to come out now. So the area, the common area between the capacitors will be smaller or larger depending on how you are turning. And that way you can change the value of the capacitance. And that is exactly what you are doing when you are pressing on the remote. When you press on the remote to switch channels, then you are changing the capacitance of your TV. So from one value to another value. So the natural frequency of the TV at that point in time, that changes. Or your set-top box, that changes basically. Then what happens is that you tune into that channel. So that is what is happening here. So this is what is called as a tuning circuit. So even though billions and billions of electromagnetic radiations are around, by adjusting this L and C values, you can change the natural frequency of this tuning circuit, and for this natural frequency, the maximum current will flow in this. Okay, so that is how you tune. And note that this tuning, or even the resonance, is possible only with an LC circuit. You must have an inductor and a capacitor in a circuit connected serially. LC. This is RLC series circuit. This L and C must be serial for you to have resonance, because this voltage and this voltage will cancel, or they will be opposing each other. So there is a possibility that at some value of XL and XC, then this voltage and this voltage will cancel, and you will have only this resistance in place. Then the maximum current will flow at that frequency. So for tuning, for resonance, L and C must be present in the circuit. You can't do it just with L. You can't do it just with C. Both L and C must be present in the circuit. Only then can you have resonance taking place in this circuit. Okay? So this is how you tune to different channels on your TV or on your radio. Hope this is clear to you. Okay, so what have we done now? So we've taken this curve so this is IM max, and this happens at the resonant frequency, and then you chosen another frequency omega 1, one more frequency omega 2, and we have defined bandwidth as 2 delta omega, where delta omega is the difference between omega 1 and omega naught, or omega 2 and omega naught. So that is the difference. So we have done that, this bandwidth. Okay, we said omega 1 is equal to omega naught plus delta omega, and omega 2 is equal to omega naught minus delta omega. And then what have we done? At this frequency, the power dissipated in the circuit would be half of the power dissipated at resonant frequency. So for that, the current that is flowing here is IM1, and that IM1 is actually equal to IM max by root 2. Okay, so this is what we have done. But what is IM max? IM max, what is IM for example? IM is simply, I'll do it here. IM is simply V by Z, Vm by Z. Okay, so this is a general formula. At resonance, Z will become R. So IM max, which is the current, maximum current at resonance, is simply Vm by R. Okay. And what is IM1? IM1 is simply Vm by Z1. Okay, what is Z1? Z at omega 1. Then what is Z at omega 1? Z at omega 1, Z1. Z1 is equal to square root of then LCR circuit R squared plus XC minus XL the whole square. So if we, I said omega 1 is here, right? Omega 1 is greater than omega naught. So if I put XC1 will be smaller than XL1 because it's higher frequency, right? So at this frequency, omega 2, XC will be greater than omega L. At this frequency, omega 2, XC will be greater than XL. But omega 1, XL will be greater than XC. So it makes sense for me to put this XL minus XC the whole square, okay, so that I get a positive value. So it doesn't matter, I can put XC minus XL itself. And when I square it, I'll get a positive value anyway. But because I've chosen omega 1, let me put XL minus XC because XL is a bigger number, so that I get positive number here itself. Okay, so this is what it is. Okay, so Z1 is this. So let's see. So what is IM1? IM1 is Vm by Z1. So Vm by Z1 is R squared plus XL minus XC the whole square. Okay. So this must be equal to, what is IM max? IM max is Vm by R, right? So Vm by R into root 2. So it is. Okay. Okay. Root 2. So I can cancel this, Vm I can cancel, and I can do the reciprocal of this, then I know that R squared is equal to this, right? So that will be square root of r squared plus xl minus xc the whole square is equal to r into root 2. So this is a condition I get. Okay, so I'm going to square this. I'm going to divide this into two parts now. I'll take this equation and then square this. What I'm going to get now? If I square this, then I get r squared plus xl minus xc the whole square is equal to r squared into 2. Okay, so that is 2r squared. So I get 2r squared. I got r squared here, I got 2r squared here. So 1r squared can be subtracted from that. Then I get xl minus xc the whole square is equal to r squared. Okay. Then clearly this is positive, so this is also positive. So xl minus xc is equal to r. So that is the condition. So xl minus xc is equal to r. When xl minus xc is equal to r, then you will have a current that will produce half the power loss as the maximum current. So this is the condition. XL minus XC is equal to R. Okay. Then let's see. What is XL? XL is omega L minus XC is 1 by omega C. In this case, omega 1. Omega 1. See this omega is taken, right? Is equal to R. But what is omega 1 anyway? So omega 1 is omega naught plus delta omega. So omega naught plus delta omega into L minus 1 by C into omega naught plus delta omega is equal to R. Okay? Well, let me take omega naught out. If I take omega naught out, then what do you get here? Omega naught into L into this will be 1 plus delta omega by omega naught for this part. What I'm going to get here? Minus 1 by, again if I take omega naught out, it's going to be omega naught to C into 1 plus delta omega by omega naught. That must be equal to R. Okay? Okay. I'm going to express C slightly differently here. Okay, what do we know? We know, so we know that omega naught is equal to 1 by root LC. So omega naught squared is equal to 1 by LC. So what is C? C is equal to 1 by L into omega naught squared. Okay? So I'm going to do it here. So that will give me omega naught L into 1 plus delta omega by omega naught and minus 1 by omega naught into, so C I'm going to have 1 by L omega naught squared multiplied by 1 plus delta omega naught is equal to R. Like that. Okay, so this omega naught cancel here, and then this L omega naught will come back up. Okay, that would give me omega naught L to 1 plus delta omega by omega naught minus omega naught L divided by 1 plus delta omega by omega naught, and that must be equal to R. Okay, so look at this. this is 1 by 1 plus delta omega by omega naught. Can I bring it up? Can I take it up? If I take this up, then I can use a particular formula. Okay, so you see, if I have 1 by 1 plus delta omega by omega naught can be written as if I bring it up, this is going to be, this can be written as 1 plus delta omega by omega naught whole power minus 1, and that can be written as 1 minus delta omega by omega naught, because this delta omega is very small quantity compared to this omega naught. Omega naught is a very high quantity and this delta omega naught will be a small number. So delta omega by omega naught is a very small number. So effectively this 1 by 1 plus delta omega by omega naught will become 1 minus delta omega by omega naught. Okay, so that is what I will make you see. So this, okay, I want you to keep this separate. Okay, so let's do this. So this equation will become omega naught L to 1 plus delta omega by 1 plus delta omega by omega naught, then minus omega naught L into 1 minus delta omega by omega naught. 1 minus delta omega by omega naught, and this must be equal to R. Okay, so if I take omega naught L out, I get 1 plus delta omega by omega naught, then minus 1 plus delta omega by omega naught. Okay, and that is equal to R. So this one and this one will cancel. So effectively I get omega naught L into omega naught is common, so 2 delta omega by omega naught is equal to R. So omega naught and omega naught get cancelled, so I get 2 delta omega is equal to R by L. Okay, so what is this? This is actually the bandwidth. Okay, so the bandwidth beta is given by R by L. So I found the bandwidth now. It is simply in an LCR circuit, the bandwidth of that circuit is given by this expression R by L. If I know omega naught, then I will get 2 delta omega as RL. So R by L, and delta omega will be simply omega naught plus half of this. That's it. In this case, my delta omega is equal to R by 2L. Okay, that's another. Okay. And what else here? So my omega 1 is simply omega naught plus R by 2L. That's all. And my omega 2 can be written as omega naught minus R by 2L. So if I know RLC value, then I can find omega naught, and I can also find omega 1 and omega 2 very easily. If I know because omega naught is actually 1 by root LC. So if I know RLC value, then I can find omega naught, I can find omega 1, I can find omega 2. Okay, so this is how I do it. So I find the bandwidth. But you see, bandwidth is alright, but bandwidth doesn't give you the entire picture. Okay? Why? That is because, suppose your omega naught is 100 and omega 1, so suppose this delta omega is 5. So what is your bandwidth now? This is 5, this is 5, so 10. You will say 10 is a bandwidth. I said, let me just take this case. If my omega naught is 100 and then if my delta omega is 5, then bandwidth is actually 10. Okay. Suppose my omega naught is 10,000. 10,000. Omega naught is 10,000 radians per second. Suppose my delta omega is 50. And what is my bandwidth now? My bandwidth is actually 100. Okay? Here my bandwidth is 10 and here my bandwidth is 100. So does it mean that this graph is sharper than this one because it has smaller bandwidth? No, it cannot be. Actually, this is sharper. Why? Because I have a bandwidth of 10 for a resonant frequency of 100. So it is about 10% bandwidth from my resonant frequency. But here, even though I have 100, what is my resonant frequency? It is 10,000. So 100 out of 10,000 is just 1%. In this case, 10%. And in this case, just 1%. So which is sharper? This is sharper. Even though the bandwidth is 100, this is sharper than this. So bandwidth per se is not the measure of sharpness. The percentage of bandwidth is the measure of sharpness. This is sharper than that one. So here the bandwidth is just 10 radians, but here the bandwidth is 100 radians. But 10 out of 100, but 100 out of 10,000. So this is sharper, this is narrower than that one. So what is the measure we can come up with? Okay, for sharpness, I can use either the percentage, I can say beta by omega naught. I can do that. Beta by omega naught. So I'll say like this is 10%. So this beta by omega naught is say 1%. So it's 10%, 1%. 1% is sharper. But you see, that is okay. You can do that. But here, the less the percentage, then the sharper it is. But if I turn it around, like if I divide omega naught by beta, then you see the greater the number, then the greater the sharpness. Right? Instead of saying beta by omega naught, which is a percentage, I say 1%, so it's sharper, and this is 10%, so it's not that sharp, it's flatter than this. I'm going to say omega naught by 100, so I get a value 100 here. If we say omega naught by beta, then we get 10 there. So now we can say that the bigger the number, the greater the sharpness. It's the same thing, but I've taken the reciprocal. So the bigger the number, then greater the sharpness when I divide omega naught by beta. But if I divide beta by omega naught, then the smaller the number, then greater the sharpness. The convention I'm going to use is this: omega naught by beta naught, beta by omega naught, so that the greater the number, then sharper the curve is. Okay? So that is what I call as quality factor. The quality factor is defined as omega naught by beta, or omega naught by 2 delta omega. So what I'm going to get here. So what is 2 delta omega? It's R by L. What is my omega naught? It's got it there, right? So my quality factor Q is equal to omega naught by R by L, so that will give me L by R. Omega naught to L by R. So this is okay. So this is important. So the greater the quality factor, the shorter the curve is. So you can tune into the frequency very well with very minimal interference, because all the other frequencies will contribute almost nothing, negligible amount, because any other frequency, omega naught, the next station would be much farther than this. I'm not going to take omega 1 as the next station, no. My next station is going to be somewhere here. So in that case, it's like this. So the next station would be this. If this is Sun TV, my Rosh TV will be here, not here. So this contribution will be much lower, negligible. So my tuning will be very efficient. Okay? So this is very important. The quality factor is defined as this. Omega naught by 2 delta omega. So 2 delta omega is R by L. So bandwidth anyway. So quality factor is omega naught L by R. Omega naught, in place of omega naught, if you put 1 by root LC, then you will have one more equation, right? So that is, you can do that too. So with Q also is equal to 1 by root LC into L by R. So that will become R into root of L by C. There is another equation. So if I know the value of R, L, C, then I can calculate, you see, almost everything. So I've chosen a resistance, I've chosen an inductor L, and I've chosen a capacitor C. From that, I can calculate my resonant frequency. From that, I can calculate my delta omega. Okay, delta omega. If I calculate my delta omega, then I can calculate omega 1, omega 2, the frequencies at which the power dissipated will fall by half from the maximum power. I can do that. And I can calculate the bandwidth. I can also calculate the quality factor. The greater the quality factor, the sharper the resonance curve is. Okay? So this is what is called as the sharpness of resonance. Hope this is clear to you.